Okay, so it looks like it caught up on YouTube and it's on and it's live now. I think we're on about a 30-second delay. So if you do send me a message via Remind to ask a question about something, there may be a few minutes of delay before I am able to get back to you. Okay, so this is Mrs. T's Chem Talk Regents Chem, and this is live stream number 1. This is going to go over some topics that I have picked because not many of you responded to me. I picked some topics that I think are most often misunderstood and most often asked about in the last few weeks of school, particularly for Regents Review. So for those of you who don't know me, my name is Elizabeth Tumanello. I'm a chemistry teacher at Calhoun High School in Merrick, New York. And I'm just going to get right in here and start going over some topics that I think are most often misunderstood in terms of Regents chemistry. So the very first thing that I wanted to go over is periodic trends. So as we look at the periodic table, we need to know that groups or families are the vertical columns. Members of the same group have the same number of valence electrons. And having the same number of valence electrons means that these members of the same group will react similarly in chemical reactions. So if I look, for example, right here, this is group 1, and from lithium down to francium, these are called the alkali metals. Group 2, from beryllium down to radium, is going to be called the alkaline earth metals. 3 to 11, sometimes people say 3 to 12, but 3 to 11 is going to be the transition metals, and 17 is the halogens, 18 is the noble gases. Noble gases are the ones that tend not to react because of their stable valence electron configuration. Helium with 2 valence electrons, neon all the way down to element 118. Each of those elements has 8 valence electrons, or a stable octet. For group 17, the halogens, these are our most active nonmetals, and in fact, fluorine is the most active nonmetal. So the closer an element gets towards fluorine, the more nonmetallic that element would be considered, and that would also be a more active nonmetal the closer we get to fluorine. When we talk about group 2, our alkaline earth metals, these alkaline earth metals are very reactive metals with 2 valence electrons, whereas my alkali metals, group 1, are our most active metals. Francium, if it actually existed in nature, it's so radioactive we don't usually see it. Francium is our most active metal, and so the closer you get to francium, the more metallic the element is, and the more active the metal is down further towards the bottom and to the left of the table. When we talk about periods, on the other hand, periods are our horizontal rows. And in the same period, the elements have the same number of shells of electrons. So in a period, it's the same number of shells of electrons. As you go across a period, you go from more metallic to more non-metallic. And that's because our metals are on the lower left-hand side here, and our nonmetals are on the upper right. We have our staircase around here somewhere, and so over here, the elements that are in this little section around here, are going to be our metalloids. I didn't exactly get the metalloids right here. We don't have a zigzag line on this particular table, but it's this general area where we have our metalloids, where the elements have both metallic and non-metallic properties. So if I clear this off again, I want to talk a little bit about our properties. I'm sorry, our trends. And so what we have trends for electronegativity. Electronegativity, remember, is the pull on the electrons. The attraction that the nucleus has for the electrons or the valence electrons in a bond with hydrogen is like the exact definition. Ionization, energy, which is the amount of energy required to remove the most loosely bound valence electron. And we have atomic radius, which is half the distance between adjacent nuclei. And all that really means is that we're measuring two nuclei, right, a nucleus and a nucleus that are next to each other, and dividing that distance in half. Because if we do the exact distance from one nucleus to the next nucleus, we get a diameter. But if we cut that distance in half, we get the radius, because remember, we can't really measure how far away those valence electrons are because there is so much empty space between the nucleus and the outermost valence electrons. So these are the three things that we tend to measure: atomic radius, ionization energy, and electronegativity. And we have trends for going across, and we have trends for going down a group. So across a period, electronegativity, that's a G, and ionization energy tend to increase. But atomic radius decreases. And the reason for these trends that we see as we go across a period is because of increasing nuclear charge. We're increasing the number of protons in the nucleus, and those positive protons in the nucleus can do a better job of attracting the valence electrons. That means we have a stronger attraction. That means takes more energy to remove those more closely attracted electrons. And that means that those electrons get closer to the nucleus, which makes the overall size decrease. Because they each have the same number of electron shells, as we go across, the pull of the nucleus on those valence electrons gets tighter and tighter, and so the atoms get smaller and smaller. As we go down a group, we see the opposite, or tend to see the opposite trend, where electronegativity and ionization energy both tend to decrease as we go down a group. Atomic radius tends to increase as we go down a group. And this is because of an increasing number of shells of electrons that shield the nucleus and the valence electrons from each other. So we say that that's an increase in the shielding effect, because as we go down a group, we're increasing the number of shells of electrons, and the only place for the next shell to go is on the outside of the one that was already there. So as we increase the number of shells of electrons going down a group, the positive protons in the nucleus become more and more shielded from the negative electrons out here. And as that shielding increases, the positive protons in the nucleus cannot hold on to the valence electrons as well. And so they hold on to them less tightly, meaning that there's less pull, less energy required to remove them, and meaning that the valence electrons become further and further away from the nucleus, which gives the increase in the radius. So across a period, all of the trends happen because of increasing nuclear charge, more protons in the nucleus. Down a group, all of the trends happen because of increasing number of shells of electrons that increases the shielding effect. The next topic that I wanted to go over, that was asked of me to go over, would be significant figures. When we count our significant figures, we can divide our measurements into Pacific or decimal present values or Atlantic decimal absent values. We said that if you have a decimal present, all of the zeros that come before the first number that's not a zero are in the Pacific Ocean, and although they need to be there for the value of the number, are not considered significant figures. So this number, or this value, I should say, the significant figures are the 5, the 6, the 0, the 4, and the 0. That would be 1, 2, 3, 4, 5 significant figures in this measurement. For this number that has a decimal point, there are no zeros leading up to the first number that's not a zero. So if there's no zeros in the front and you have a decimal present, every single number is part of the significant figures. 1, 2, 3, 4, 5, 6, 7 significant figures in this particular measurement. So it's only zeros at the beginning that aren't part of the significant figures if we have decimal present. If we have decimal absent, on the other hand, any zeros that are on the right-hand side after all of the numbers that aren't zeros are in the Atlantic Ocean and are not part of the significant figures. So for 1500, only the 1 and the 5 count as significant figures. The other two zeros need to be there in order to make the number 1 in the thousands place, but the zeros are not part of the measurement. So this measurement has 2 significant figures, and this measurement here has 4 significant figures. You are going to count starting with the first number that's not a zero, that's all the way closest to the Atlantic Ocean. So these zeros are in the Atlantic Ocean. This 0 is in the Atlantic Ocean because this is not a 0 and this 5 is not a 0. That's how we know to start counting significant figures there. So zeros in the ocean side, 0 on the ocean side. Everything else going inland is part of the significant figures. Just going to pause here for a second to make sure that the audio is coming through on YouTube. So just give me about 2 to 5 seconds and I'll be back. Okay, I have a visual of what is going on my other iPad here, but I couldn't tell whether or not the audio was coming through. So I just wanted to make sure that you were able to hear everything that was going on. I didn't want to find out at the end of the hour that you had no audio. The next thing that was asked of me to go over would be to review bonding. This is something that people tend to ask about constantly because it is a difficult topic. So I want to make sure that we are able to go over this one fairly, fairly in depth. So when we start with our bonding, metallic bonding doesn't really need a whole lot because metallic bonding is just in metals. When we talk about metallic bonding, we're talking about single metals. So something like magnesium has metallic bonding, or something like sodium has metallic bonding. Metallic bonding is the one that has the mobile electrons it has luster, it is, metals are malleable, metals are ductile, all because of these mobile electrons. We define metallic substances or metallic bonding as positive ions and a sea of mobile electrons. And because of these mobile electrons, metals are going to conduct in any phase. So solid, liquid, gas, metals would conduct because their electrons are always mobile. Ionic bonding is when electrons are transferred. These electrons are usually transferred from a metal to a nonmetal, because remember, metals tend to have low electronegativities and nonmetals tend to have high electronegativities. So the metals are going to give their valence electrons away to the nonmetals in these ionic bonds. When we talk about these ionic bonds, their properties, they tend to be hard, they have high melting points, and they are going to conduct electricity in liquid or aqueous solutions only. That is when they have mobile ions. So notice, for ionic substances, they conduct in liquid and solution because that's when their ions can move. For metals, they conduct all the time because their electrons can always move. For covalent bonding, that's going to be sharing electrons between nonmetal atoms. So these electrons are shared between nonmetals because nonmetals are going to have such a strong electronegativity or high electronegativity that they pull on those electrons so tightly that no one atom can take them away from the other. For covalent bonding, we have nonpolar covalent bonds, and we have polar covalent bonds. Nonpolar bonds are equal sharing. Polar bonds are unequal sharing. And these nonpolar bonds, this equal sharing, would be between atoms of the same element. Because they have the same electronegativity, they are able to pull on the electrons with equal strength, so that results in an equal sharing. That would be like our Brinkelhoffs. Remember we said our diatomics, like Br2 has a nonpolar covalent bond, I2, N2, Cl2, H2, O2, and F2. These all have nonpolar covalent bonds. And we also have nonpolar covalent bonds in our carbon-to-carbon bonds, like in an alkane or in an alkene or in another ionic compound. For polar bonds, these are unequal sharing. I have a question that came in, which I'll go over for Carolyn. I'll go over that question after I finish this polar covalent bond, to go back to the question about ionic. So we talk about these polar bonds. We're talking about unequal sharing. That would be like in HCl. That bond would be an unequal polar covalent bond. When we talk about something like our organic compounds, the bonds like between C and O in an aldehyde here, like this is ethanol, that would also be an unequal sharing. When we talk about our covalent substances, the properties is that they tend to be soft, they tend to have low melting points, they tend to be non-conductors because they never have mobile electrons and they don't make ions. We also make molecular substances when we have covalent bonds. So if they use the term molecular substances, you're looking for something that has covalent bonds. So the question that came in is that when you have to look for an electrolyte also, you look for ionic. So because when they use the word electrolyte, we are talking about something that when it dissolves in water, so when we make it into an aqueous solution, we will conduct electricity. So yes, ionic compounds that are soluble are electrolytes. The other things that are electrolytes, just to go into this question here, would be acids and bases. So these are the other things that are considered electrolytes, acids and bases, but anything with mobile ions in solution, which would be an ionic compound in solution that's soluble, or an acid or a base, would be considered an electrolyte. So the next concept that was asked to I was asked to go over would be the naming and the formulas. So here I have a couple of formulas here that these are all ionic. I can tell that they're ionic because it's either a metal with a nonmetal, or I can tell that something is ionic because it's a metal plus something from table E, or something from table E plus a nonmetal, or, too many ors here, two things from table E together. And just because I just mentioned table E so many times, let's just look quickly at table E. Table E is our table of polyatomic ions. And when we look at table E, all of these polyatomic ions can be part of an ionic compound. So when we have something from table E in a formula, we then also have an ionic compound, and we're going to use these things on table E in ionic compounds the same way that we use the same way that we treat our metals and our nonmetals. So any of the positive ions on table E could take the place of a metal in a formula. Any of the negative ions on table E could take the place of a nonmetal in an ionic formula. So when we look at Na2SO4, Na's name is sodium. And SO4, if we switch back to table E, oops. If we switch back to table E, SO4, its name is sulfate. It's down here, okay? So this here would be called sodium sulfate because you never change the name of a metal in an ionic compound formula, and you use the name from table E for the sulfate. For an ionic compound that just has a simple metal with a nonmetal, we're going to say the name. We're going to say the name of the metal, which, remember, if you don't know the names of your elements, you're going to look on table S. Table S has names, atomic numbers, symbols, a whole bunch of other information. And you're going to say the name of the nonmetal, but because this is ionic, the nonmetal is the negative ion, and so we change the ending to IDE. This IDE ending means negative ion. And anytime we have an ionic compound, the metal is always the positive ion, and the nonmetal is the negative ion. We said, though, for things like iron and copper, which are transition metals, we need to identify which charge is being used because, as we get down to the periodic table, members of the transition metal groups tend to have multiple oxidation states. Did I go? Here we go. Members of the transition metal groups tend to have multiple oxidation states, and any of these elements that have more than one oxidation state, like iron has a +2 or a +3, copper has a +1 or a +2. Remember, we need to give them a middle name in our formulas. So iron can either be iron parentheses Roman numeral 2 or iron parentheses Roman numeral 3. Copper is either copper parentheses Roman numeral 1 or copper parentheses Roman numeral 2. And we need to do that in order to specify which ion is being used in the formula. So when I look at this, I know that on the periodic table, chlorine has its negative charge as a -1, which means here, iron's charge must be a +2 because of the crisscross. So this is called iron Roman numeral 2 chloride. Whereas here, if I look up sulfate on table E, SO4 has a -2 charge. So in order for there to be no subscripts anywhere, that means that this copper has a +2. So I'm going to call this copper Roman numeral 2 sulfate. And if I was given the name, let's say I had aluminum sulfate or iron 2 phosphate, the ATE would let me know that I was looking for something from table E. If I had something like magnesium fluoride, the IDE would tell me nonmetal, negative charge, periodic table. So I'm going to look up the metal's positive charge, and I'm going to look up the nonmetal here's negative charge on the periodic table. Crisscross, drop the signs, reducing the numbers up here if I can before I crisscross, and ones do not need to be written, so this becomes MgF2. For aluminum sulfate, I look up aluminum on the periodic table. Its charge is a +3. I look up sulfate on table E and put it in parentheses. Its charge is a -2. Crisscrossing the number outside the parentheses, I get Al2, parentheses SO4, 3. For iron 2 phosphate, that means I'm using irons +2. Anytime they give you parentheses, that is the charge. We don't have to look anything up on the periodic table for that. And this ending in ATE, I look this up on table E, and it says it has a -3 charge. I crisscross this number outside the parentheses, and I wind up with Fe3, parentheses PO4, 2. I'm going to do one more example just so we can see one that doesn't need parentheses. Let's do sodium nitrate. I look up sodium's positive charge. I look up nitrate, ATE, on table E. I notice that these charges are equal and opposite, so they cancel, and NaNO3 is my formula. Remember that you should have an open remind message from me because I just sent you a message prior to the video, prior to the live stream. So if you have any questions, please feel free to just respond to that. And those messages are just coming directly into my email so I can answer those questions in the video. You're about 30 seconds behind where I am. So if a question comes in and I'm already past that part, I will absolutely go back to it when I have the next chance. The next thing that was asked for me to go over would be balancing equations. And what I like to do is inspect and look and see how many atoms of each type are on each side first. But the reason why we need to balance equations is because of the laws of conservation of matter. And every reaction has a balance or a conservation of mass, energy, and charge. So every reaction has a balance of mass, energy, and charge. We would have, if a balanced equation is balanced properly, we have the same number of atoms or the same number of moles of atoms on each side. Remember that the law of conservation says that matter cannot be created or destroyed. It will only change forms in chemical reactions. So I'm going to inspect and I'm going to see how many atoms of each kind are on each side. So here I have H2, so that means that there's 2 moles of atoms of H in the reactants. Here I have H2, so there's 2 moles of atoms of H in the products. O2 means 2 moles of atoms of O. O with an understood subscript of 1 means there's 1 on this side. What that means is that we are out of balance. If all of these numbers matched up within the same line, we would be balanced and we wouldn't have to do anything. But I need to put a 2 in front of here to get these O's equal, but then that also multiplies by the H's. 2 times that 2 gives me 4 H's. And in order to get there to be 4 H's on each side, I can put a 2 in front of this H2, and that makes them match up. This is an understood 1, and you can either put that in or not put that in. That doesn't need to be there. In this reaction, if I wanted to see, so I have C's, I have H's, and I have O's. This one happens to be combustion. Over here, this one was synthesis. And in our combustion reaction, we are going to balance in a special order. We're always going to do the C's first, then the H's, then the O's last, because the O's are in 2 places here. So the numbers that we put, we can put a number here to balance out all the O's. The O's are in 2 places here also. So if we try to start with the O's, we're going to kind of go in we might go in some circles. So there's 6 C's on one side and 1 on the other. We have 12 H's on one side and 2 on the other. And then I have 6 plus 2. I have 8 O's on this side. I have 2 plus 1. I have 3 O's on the other side. So I'm going to go ahead and balance my C's first, and I'm going to put a 6 in front of the CO2, which gives me 6 C's. But then that's 12 plus 1. That's 13 oxygens, I should say. Balance my H's next. I'm going to put a 6 here. So that multiplies by 2 to get 12 H's. But now I have 6 times 2, I have 12, plus 6, I have 18 O's. I can't put a number here, because if I put a number here, that would balance, take this out of balance. So I'm going to put a number here so that my 6 plus something equals 18. 6 plus 12 equals 18. So this coefficient becomes a 6. This is an understood 1. Now, when I add them all up, it's the same amount on each side. And for combustion, you're always going to do that. You're always going to do C's first, then H's, then O's. The next thing that we want to go over, or that I want to go over, is the heating and cooling curves. So if we look at the heating curve, we will always be, because any graph that's talking about energy that goes uphill is called endothermic. This one is, it starts low, the ending point is high. This is also an endothermic energy graph. This goes for the potential energy graphs also. So like anything that starts low and ends high would also be endo. So we're always going to have temperature versus progress or time, or sometimes down here, it'll say heat added. And when we have a slanted line, this means that the temperature is going up. Don't forget that temperature measures average kinetic energy. So as we have an individual phase, it's the kinetic energy that is increasing. So when it's just a solid or just a liquid or just a gas, it's the kinetic energy that's changing. When we look at the phase changes, The phase changes, we have no temperature change. So melting or fusion, condensation or boiling are the names of the phase changes. Solid to liquid is called melting or fusion. Liquid to gas, oh my goodness, I put condensation there. That's not what that is. Liquid to gas, sorry about that, is vaporization. Or boiling. So evaporation is not the same thing as boiling, but vaporization and boiling are the same thing. That's the name of the phase change between liquid and gas. When something is going through a phase change on the endothermic heating curve, the potential energy is increasing. So on the heating curve, you only have either kinetic energy changing or potential energy changing. We never have both changing. Now, when we have melting or fusion, we would use the formula Q equals MHF, which we would use table T and B together for that. When we have boiling or vaporization, we would use Q equals MHV. And again, it's tables T and B that give us the information for that. Anytime there is a temperature change, we're going to use the formula Q equals MC delta T. And Q equals MC delta T, again, same tables found on table T, and the constants are found on table B. Remember, delta T means temperature change. So if the temperature is changing, it's MC delta T. If phase changes, it's either HF or HV. So to go over the opposite, which would be the exothermic curve, again, going downhill means it's exothermic, just like in the potential energy diagrams. Overall, downhill means exothermic. We are going to have, again, one phase when the temperature is changing and a phase change when the temperature is not changing. Because this is exothermic, the kinetic energy is decreasing when the temperature is decreasing. And it's the average kinetic energy that's decreasing. And the potential energy would be decreasing for the phase changes. The name of the gas to liquid phase change is condensation. The name of the liquid to solid phase change is freezing, or you might also see solidification. Remember, at any point during this live stream, you can feel free to send me an email. Send me a remind message. You should have an open remind thread. Everyone who's in one of my remind groups got a remind message from me at the start. So you should have something to respond to. Send me a message there if at any point there's something you need me to go over. So for potential energy diagrams, they usually look like this. They're measuring the progress of reaction versus potential energy. This one is going downhill overall. So this one would be exothermic. That means that we would have reactants making products with energy in the products, and the value of the delta H is going to be negative because it's exothermic. We always plot the heat or potential energy of the reactants at the beginning. The activated complex is this high point, and the products are the furthest right. The reaction always goes for the forward is always left to right. We have a couple of different types of values. We have ones that hit the x-axis, which would all be measuring potential energies of whatever they go up to the height of. This would be the potential energy of the reactants here, potential energy of the products here, potential energy of the I'm misspeaking. Go backwards for a second. Potential energy of the reactants here, potential energy of the activated complex here, potential energy of the products here. Okay, whatever they go up to the height of is what they're measuring the potential energy of. The products could go anywhere up to this line. Potential energy of the reactants could go anywhere up to this line. And potential energy of the activated complex could go anywhere up to this line. We also have some values that go to the top above the curve. I don't know why this is starting to delay. Here we go. So this here would be the forward activation energy. And above the products to the top would be the reverse activation energy, because this is how much energy the reactants have to get to go forward. This is how much energy the products have to get to go backwards to get up to that top point. The last value that we said we have on here is our delta H. And remember, we visualized top bun, bottom bun, and delta hamburger. So anything that goes in this section from the height of the products to the height of the reactants is going to be our delta H, and it's defined as the potential energy of the products minus the potential energy of the reactants, and that's how we get the delta H value. Next thing I wanted to go over was LeChatelier's principle. And first thing we need to know that LeChatelier's principle deals with systems at equilibrium. And we have phase equilibrium when we have a phase change. So phase equilibrium is at a phase change on the heating and cooling curves. We have solution equilibrium for a saturated solution. So those are the table G questions. And the ones that are on the line for the substance, those would be also solution equilibrium. And we can have chemical equilibrium for a reaction that is reversible. When we are at equilibrium, we have reached a state where the forward and the reverse are at equal rates, and the reactants and products are at constant concentrations. So when we're at equilibrium, we've reached equal rates and constant concentrations. When we've reached this situation, if we apply a stress to a system, we will have a shift in the equilibrium, which will alleviate the stress. And we used add away and take towards to predict this. We also said that if you increase the pressure, it shifts to the side with less gas. So for example, if I have 2H2 gas plus O2 gas in equilibrium with 2H2O gas. The double arrow, remember, means that it's reversible and at equilibrium. And they say, what is the effect of the effect on the system if we add H2 gas? We should also put plus heat over here. It's exothermic. If I add H2, this is my left side, right? This is my right side. Add away. I'm going to shift right. I'm going to make more H2O, and I'm going to use up O2 in the process. What if I remove O2, take out O2, shift towards? That means I'm going to shift left. If I shift left, I make more of what's on that side, which is H2, and I use up water to get there. If I increase the temperature, I talk about the heat. If I decrease the temperature, I talk about the heat. So wherever the energy term is, that's how you determine whether you're shifting towards or away from. Adding heat, you shift away from where the energy is. Removing heat, you shift towards. And if I increase the pressure, I shift to the side with less moles of gas. 2 plus 1. This side has 3 gas. 2 gas on this side. So increasing pressure, I shift to the side with less gas. I'm going to shift right. Increasing the amount of water, decreasing the amount of H2 and O2. The next thing that I wanted to go over was finding atomic mass. The average atomic mass, remember, atomic mass is on the periodic table, and it is based on the percent abundance and the masses of the naturally occurring isotopes. And it's a weighted average. So if I have a random made-up element like element X, and element X has 2 isotopes, element X's isotopes are 40 and 42. And it's 95% X40, which has a mass of 40.10, and it is 5% of X42, which has a mass of 42.03 atomic mass units. We're going to take the percent times each of these and get a number. And when we get that number, we're going to write it down and we're going to add those numbers up. So I'm just going to put the calculator on the screen so I can do that. So in order to multiply by the percent, you can either press the percent on your calculator or move the decimal point back 2 places. So I'm going to do 40.10 times 95%, and I get 38.095. And I'm going to clear that. So I gotta go back to mouse. I'm going to clear that, and I'm going to do 42.03 times 5%, or if I wanted to move it back, I would do 0.05, and I get 2.1015. I add these things together, So 2.1015 plus 2.1015 plus 38.095, and my average atomic mass for this made-up element would be 42.298 atomic mass units. So you multiply percent times the mass, and the other method that you could have used instead of pressing the percent in your calculator is that 95% is equal to 0.95. Instead of pressing the percent, you could multiply by 0.95. Instead of pressing the percent, you could have multiplied by 0.05, or you could have multiplied the two and then divided the whole thing by 100. But either way, there's no dividing in a weighted average. You're going to multiply mass times percent, and then add up the results. The next thing that I wanted to go over was nuclear reactions. Remember that nuclear reactions give off a tremendous amount of energy. And this is because in every nuclear reaction, we have some mass, very, very small amount of mass, converted into energy. We have table N for natural nuclear, and on table N, you can see whether something will naturally undergo alpha, beta, or positron decay. You also have on table N your half-life times, the amount of time for a half-life. And you can look at that. Every time a half-life goes by, the amount of remaining isotope that's unchanged divides in half. The two that I wanted to mainly go over that everybody usually confuses or that I get a lot of questions about are fission and fusion. And remember, fission is splitting, fusion is uniting. In fission, you're going to see neutrons plus something with a really high mass number, like uranium-235, with two pieces that it's split up into, plus 2 or 3 more neutrons. So neutrons on both sides are going to tell you fission. Whereas fusion, almost always the way that they show it is either 2,1H over 2,1H makes 4 over 2He, or 2 over 1H, that's deuterium, hydrogen 2, plus 3 over 1H, which is tritium or hydrogen 3, makes this plus another neutron. So if it's ever fusion, it's usually H plus H makes He. Even if there's a neutron in the products, don't be confused. And because we are uniting in fusion and we're putting together things with mass numbers, with nuclei that are of equal charge, we need tremendous energy and tremendous pressure to put them together because they repel each other. Whereas fission is the one that is used in power plants, and fission is the one, if it's left out of control, can cause an explosion for a bomb or a nuclear meltdown. The next topic would be half reactions for our redox chapter. So if we have a reaction like Na plus PbCl2 makes Pb plus NaCl, the first thing you might notice is that it's not balanced. We're actually not going to balance it here. We're going to balance it when we do the half reactions. So the first thing to do is to plug in our oxidation numbers. Remember, metals or nonmetals that are by themselves with no charge written, that would be considered to be a charge of 0. That would be an atom that has no charge. So we put those in, and then we go through and we find the other oxidation numbers. Because these are ionic compounds, the chlorine is going to be a -1. Sodium here is +1 to get to 0. Because this is also still a -1 times 2 is -2, has to add up to 0, so that makes Pb +2 here. Chlorine, or I should say chloride, is my spectator, so it's not going to be brought down for the half reactions. So I separate out the different elements, what they look like before the arrow, and what they look like after the arrow. So I have sodium going up to +1, that's losing electrons, oxidation because the charge increased. Lead +2, or lead 2, is going down in charge. So that we are going to label gaining electrons is reduction because the charge is going down. I have a question coming in that asks about natural and artificial nuclear reactions. I will go back to that as soon as I finish with the half reactions. With the losing electrons oxidation, the electrons have to go in the products because they are given off. Has to be the same number of electrons that is the difference in charge. For gaining electrons reduction, the electrons go before the arrow. Again, it's the same number as the difference in charge. Now, because this half reaction only has 1 mole of electrons and this half reaction has 2, we need to get the numbers of moles of electrons to be equal in each of the 2 half reactions. So this one gets multiplied by 2. This one gets multiplied by 1. When I distribute it out, it's 2Na0, 2Na+1, 2 moles of electrons, which now we have the same number of electrons in each half reaction. And that means that up here, if I want to go back and balance this, anywhere that I have my Na, it has to be a 2. That's a way to go back and balance after you've seen that. So for nuclear reactions, natural versus artificial, natural has 1 reactant, and artificial has 2 reactants or more. So artificial, we have to bombard the nucleus with a high energy particle to cause it to happen. Fission would be artificial because it's the uranium-235 plus the neutron. That would be our 2 reactants. And for natural, let me just go here for a second and just pick one out. Just have to get to table N. For example, if we do carbon-14 has beta decay. So natural, because it's on table N, the carbon-12 would be the only reactant, give off that beta particle, and turn into nitrogen-7. Because it's on table N for natural nuclear, that's what I use the N for. That means that it just gives off this one beta particle. Right, we can look that up on table O, and 7 minus 1 is 6, 14 and 0 is 14. So there might be more than one product, but there's only ever one reactant in a natural nuclear transmutation. For neutralization and titration, remember we can use titration in order to determine the unknown concentration of an acid or a base by using a volume of a known acid or base. And for neutralization, anytime you put an acid plus a base together, remember acids tend to start with H, bases are going to be metal plus OH. We're always going to make water as one of the products, and then the positive and negative pieces that were not H and OH from the acid and the base, we're going to crisscross and drop the signs to get the formula for the salt. If we had like H2SO4 plus KOH, we would still do this and make water. And then the K and the SO4, we would crisscross and drop the signs. And because SO4 has a -2 charge on table E, it would become K2SO4. And then we'd have to go back and put coefficients to balance, but we don't wind up with salts with H's and OH's in them just because there's a 2 here or a parentheses and a number here. So we might have a question that says, find the concentration of HCl if 20 milliliters of 0.1 molar sodium hydroxide completely neutralize 10 milliliters of hydrochloric acid. 20 milliliters of 0.1 means that those two numbers go together. The 10 is going to go with my X. The formula, MAVA equals MBVB. The molarity of the acid is what we're looking for. The volume of the acid is 10 milliliters. Molarity of the base is 0.1 molar. Volume is 20 milliliters. But even if I didn't know which side was acid and which side was base, that would be fine. No big deal. I would just know that the 20 milliliters of 0.1 goes together, and that makes the 10 go with X. When 10X equals 2, I get X equals 0.2 molar as my answer. I just did redox reactions and half reactions. I guess I didn't realize I put this in here twice. So let's go to the voltaic cell. When we talk about the voltaic cell is spontaneous. It converts chemical energy to electrical, and redox reaction gives off electricity. For a voltaic cell, the more active metal on table J is the anode. A general sketch of a voltaic cell would have 2 pieces of metal dipped in solution, connected by a wire, with a salt bridge and solutions in each container. The salt bridge, remember, is for the ions. The wire is for the electrons. We have an anode, which could be on the left or the right, and a cathode. The anode is always the site of an oxidation. The cathode is always the site of reduction, and the cathode always gets bigger. Electrons flow in the wire from anode to cathode because anox is losing electrons, oxidation, and the charge goes up. Big red cat is gaining electrons, reduction, and the charge goes down. The size of the anode always gets smaller because atoms are turning into ions. The size of the cathode always gets bigger because ions are turning into atoms. And the half reaction for oxidation would always happen in this cell right here. The half reaction for reduction would always happen in that cell there. For electroplating, in electroplating, this would be a electrolytic cell. Electrolytic cells need a power source because they are non-spontaneous. They need a power source because they are non-spontaneous, which means that you'll usually see a battery or a power source here. We are converting electrical to chemical energy, and electricity is causing a redox reaction. When we do this, we will usually see one container where there's an object like a spoon, a fork, a necklace, I'm going to say a ring here, connected by a wire to a power source, and then also a piece of metal connected by a wire to a power source. And the piece of metal, let's say we are silver plating this ring. This needs to be connected. There will be a solution of electrolytes in there. And from my power source, my ring here would be my cathode. My piece of metal is always, my object is always my cathode. My piece of metal is always my anode, and it's still, anode is the site of oxidation, and the cathode is the site of reduction, and the cathode is where atoms are added to the outside. The object will always be connected to the negative side of the battery or the power source, and the piece of metal will always be attached to the positive side of the power source or the positive side of the battery. What we're actually going to have happen in electroplating is that the same metal is both oxidized at the anode and reduced at the cathode. So the metal is oxidized here, and the ions travel in the solution to the ring, and the electrons travel through the wire to the ring. So the atoms and the electrons, I should say the ions and the electrons meet back at the object, and they make atoms again on the surface. So I am going to stop here. This is going to be the end of live stream 1. If you are not watching this live, you can pause, you can rewind, you can watch this over and over again. You can use this also as a source of other questions to send me, because there will be another live stream video on Monday at about the same time. So please feel free to send me messages on Remind, or send me an email or something like that to make sure that you get your other questions asked in the second live stream. Don't forget that you can also find more videos on Mrs. T Chem Talk YouTube and Tomanello chemistry.weebly.com is my website, where you can find links to all the videos as well. So hopefully your studying is going well. Hopefully this was helpful for you, and happy studying for the rest of what you're doing here.